Hello. I'm going to go through the OCR 2023, AS Level, Chemistry, Paper 2, Depth in Chemistry. If you find this video useful, please click like, and leave a comment, as it will help me to carry on making more videos like this. In the fixed comment under the video, I leave a link to my website jctnotes.com where you can see the written answers to this paper. Question 1 is about titanium, atomic number 22, and its compounds. In part A, we have a table with the abundance of isotopes of a titanium sample and 3 questions. In the first question, we are asked to calculate the relative atomic mass of the sample, giving the number to 2 decimal places. To calculate the relative atomic mass of titanium in the sample, we use the weighted average of the isotopic masses based on their abundance percentages. We multiply each isotope's mass number by its abundance percentage. We add all these products together. I get 471.80. We divide this sum by the sum of all the percentages, that it should be 100, as the whole sample is titanium. This gives 47.918. Rounded to 2 decimal places gives 47.92. In the second question, we are asked to complete the electron configuration of a titanium atom. We are given the first term as 1s2. As the atomic number, that is the number of protons, is 22, the neutral atom has 22 electrons and the electronic configuration can be filled by using the energy level diagram with these 22 electrons. Alternatively, using the periodic table, we can see that the titanium is a transition metal of the 4th period, therefore, it is going to have the orbital 4s filled and we fill the orbital 3d with 2 electrons. The answer is. The last question asks to complete the table to show the number of protons, neutrons, and electrons in an ion of titanium-48 with 2 positive charges. As the atomic number of titanium is 22, the number of protons is 22. The problem asks for the isotope 48, then, number of protons plus number of neutrons equals to 48, therefore, the number of neutrons is going to be 48 minus 22 equals to 26. Finally, since titanium 2+ is the ion form, the atom has lost 2 electrons from its neutral state of 22 electrons. Thus, the number of electrons is 22 minus 2 equals to 20. In part B of question 1, we are given the process to purify titanium from titanium oxide and we have 3 questions. In the first question, we are asked what is the systematic name of titanium oxide. Transition metal cations with multiple possible charges are labeled with Roman numerals in parentheses to indicate their specific charge. Hence, the systematic name is titanium-4 oxide. In the second question we have that the percentage yield of titanium from titanium chloride is 72%. We are asked to calculate the minimum mass, in kilograms, of sodium that is needed to produce 1 kilogram of titanium, giving the answer to 3 significant figures. To obtain 1 kilogram of titanium with a 72% yield, we need to aim to get 1.39 kilograms of titanium. Using the molar mass of titanium as 47.9 grams per mole, and changing from kilograms to grams, we can get that 1.39 kilograms of titanium is 29 moles of titanium. From the stoichiometry, we need 4 moles of sodium for every mole of titanium, therefore, to get 29 mole of titanium we need 116 moles of sodium. And using the molar mass of sodium as 23 grams per mole, we need 2,668 grams of sodium. Expressed in kilograms and with 3 significant figures we have 2.67 kilograms of sodium. In the third question, we are asked how titanium could be separated from the sodium chloride mixture in reaction 1.2 at room temperature. We can use that the sodium chloride is soluble in water, while titanium is not. Therefore, the titanium can be separated from the mixture by dissolving the sodium chloride in water, filtering the solid titanium, and then drying it. Question 2 is about some elements in period 3 and compounds they form. In part A, a student adds a small piece of calcium to a beaker containing an excess of water. And we have two questions. In the first question, we are asked to construct the equation for the reaction and predict one observation that the student would make. The reaction of group 2 metals calcium, strontium, and barium with water produces the metal hydroxide and hydrogen gas. The magnesium with cold water produces the same reaction, but hot magnesium does react vigorously with water in the form of steam to make magnesium oxide and hydrogen gas. Beryllium is no reactive with water at room temperature. Therefore, the reaction is calcium plus 2 of water to give calcium hydroxide and hydrogen. About the observation, any of the following observations would give you the second mark. Formation of bubbles. The solid calcium dissolves. A white precipitate forms. This is accepted as correct in the marking scheme, although it depends on the proportions of calcium and water used by the student. In the second question, we are asked to suggest one difference that the student would observe in the reaction of barium with water compared to the reaction of calcium with water. As the barium is more reactive than calcium, any of the observations mentioned above will be produced faster. One of the following will answer the question. The barium will produce more vigorous formation of bubbles. The solid dissolves faster. The white precipitate forms faster. As mentioned before, this is accepted as correct in the marking scheme, although it depends on the proportions of metal and water used by the student. In part B of question 2, we have a student with a mixture of sodium chloride and barium nitrate and a solution of sodium sulfate. We are provided with the method that the student uses to determine the percent by mass of the sodium chloride. We have three questions. In the first question, we are asked to write the equation for the formation of barium sulfate in step 2, including state symbols. To start with the reaction, I write the information that I have, bearing in mind that as the mixture sodium chloride and barium nitrate has been dissolved in water, both of them are in aqueous state. We also have the sodium sulfate solution. As product, we have a precipitate of barium sulfate. Now, we have a look what is common on both sides of the equation to identify what is missing and what is not needed. We can see that in the products and in the reactant we have barium and sulfate. The barium comes from the barium nitrate, therefore, we are going to have two nitrate ions in the products. The sulfate is provided by the sodium sulfate, therefore, we are going to have two sodium ions as products. We can put together the ions of sodium and nitrate to form 2 moles of sodium nitrate in aqueous state. The sodium chloride does not participate in the reaction, we can eliminate it. Therefore, the reaction is barium nitrate aqueous plus sodium sulfate aqueous to produce barium sulfate solid plus 2 of sodium nitrate aqueous. In the second question, we have that the student obtains 3.28 grams of precipitate. We are asked to calculate the percentage by mass of sodium chloride in the 5 grams mixture, giving the answer to 3 significant figures. With the mass of the precipitate and its molar mass, we can calculate its number of moles. I get 0.014053 moles of barium sulfate. I use at least 3 significant figures to minimize rounding errors. With the stoichiometry of the reaction, 1 mole of barium sulfate requires 1 mole of barium nitrate, therefore, the student started with 0.014053 mole of barium nitrate. As the molar mass of the barium nitrate is 261.3 grams per mole, the initial mass of barium nitrate is 3.672 grams. The rest of the 5 grams is sodium chloride, then, its percentage is 25.56%. Rounded to 3 significant figures, it is 26.6%. In the third question, the student changes the method by adding an excess of silver nitrate solution instead of sodium sulfate. We are asked to explain whether this change would allow the student to determine the percentage by mass of sodium chloride in the mixture. The addition of silver nitrate instead of sodium sulfate will produce a precipitate of silver chloride, not barium sulfate. This will allow the student to determine the percentage of sodium chloride from the mass of the silver chloride precipitate. In Part C, of Question 2, we are provided with a table showing melting points and electrical conductivities of some elements in period 3 and their compounds, and we have 2 questions. In the first question, we are asked to complete the table to show the type of lattice structure of each substance. Magnesium sulfide is a compound formed by ions of the metal magnesium and of the nonmetal sulfur. This combination produces ionic bonding between these ions. The structure is giant ionic. Aluminium is a metal, therefore the structure is giant metal. Silicon is a typical giant covalent structure. Phosphorus chloride is a compound formed by 2 nonmetals forming a single covalent or simple molecular structure. In the second question, we are asked to explain why the magnesium sulfide has a higher melting point than phosphorus trichloride and why aluminium has a greater electrical conductivity than silicon. Melting point: in ionic bonds, like the magnesium sulfide, there are strong electrostatic attractions between the positively and negatively charged ions, requiring a lot of energy to break, resulting in a high melting point. On the other hand, in simple molecular structures, like the phosphorus trichloride, the molecules are held together by relatively weak van der Waals forces. These weak forces require less energy to overcome, resulting in a lower melting point. Conductivity: the aluminium presents a metallic bonding with delocalized electrons. When a voltage is applied, these electrons move easily through the metal, resulting in high electrical conductivity. On the other hand, in the silicon, each silicon atom is covalently bonded to 4 other silicon atoms forming a giant covalent structure. All valence electrons are involved in these covalent bonds, leaving no free electrons to conduct electricity. Question 3 is about halogens and halogen compounds. In Part A, we have seawater containing a concentration of potassium iodide of 0.150 grams per cubic decimeter. Iodine can be extracted by bubbling chlorine gas through seawater. We are asked to explain why chlorine is more reactive than iodine and determine the volume, in cubic decimeters, of seawater that is needed to manufacture 1 ton of iodine. When chlorine gas is bubbled through seawater, it displaces iodine from iodide ions due to chlorine's higher reactivity. Chlorine is more reactive than iodine due to several factors. Effective nuclear charge: chlorine has smaller size and higher effective nuclear charge, meaning that it can gain electrons more easily. Electronegativity: chlorine has a higher electronegativity compared to iodine, meaning chlorine has a greater tendency to attract electrons towards itself. Atomic size: chlorine has a smaller atomic radius, resulting in a stronger attraction between the nucleus and the outermost electrons. The calculation of the volume of potassium iodide needed to produce 1 ton of iodide involves a chain of units conversions and moles proportions. There are different ways to solve this problem. My first step is to calculate the molar masses of iodine, 253.8 grams per mole, and potassium iodide, 166 grams per mole. From the stoichiometry of the reaction, we have that 2 moles of potassium iodide produce 1 mole of iodine. With the use of the molecular mass, this translates that to obtain 253.8 grams of iodine we need 332 grams of potassium iodide. As 1 ton is 1 million grams, 1 million grams of iodine is equivalent to 1.308 by 10 to the power of 6 grams of potassium iodide. And with a concentration of 0.150 grams per cubic decimeter, we need 8.72 cubic decimeters. In part B of question 3, we have the reaction of chlorine reacting with calcium hydroxide to form calcium hypochlorite, CaOCl2, and calcium chloride. We have the statement that this is a disproportionation reaction, and we are asked to state what is meant by disproportionation and use oxidation numbers to show that disproportionation has taken place. Disproportionation, or dismutation, is a redox reaction where one compound is oxidized and reduced in the same reaction. To explain the disproportionation, we need to refer to the oxidation numbers. Let's find these numbers. Chlorine atom in the molecular chlorine has an oxidation number 0 as it is in its natural form. In the calcium chloride, the calcium has an oxidation state +2, as the calcium chloride is neutral. Both atoms of chlorine compensate the +2 of the calcium, making the oxidation number of each chlorine -1. In the calcium hypochlorite, the calcium has an oxidation state +2. This means that each of the two hypochlorite has a negative charge. As the oxygen has an oxidation number -2 and the ion has a -1, the chlorine has a +1 oxidation number. Therefore, this is a disproportionation reaction because the chlorine with oxidation number 0 in the molecular chlorine has been reduced to oxidation number -1 in the calcium chloride and oxidized to oxidation number +1 in the calcium hypochlorite. In part C of question 3, we are given the alkaline hydrolysis of 2-bromopropane. We are asked to outline the mechanism for the alkaline hydrolysis of 2-bromopropane using the curly arrow model, showing the relevant dipoles and lone pairs, and naming the mechanism. Many of the reactions of halogenoalkanes are nucleophilic substitutions SN. Depending on the structure, the mechanism can be SN1, tertiary halogenoalkanes, or SN2, primary halogenoalkanes. Secondary halogenoalkanes can proceed through a combination of both SN1 and SN2 reactions depending on their specific structure. The marking scheme allows SN1 and SN2 mechanism in this exercise. For SN2, nucleophilic substitution reactions rely on the polarization of the carbon-halogen bond. This occurs because the halogen is more electronegative than the carbon atom, resulting in the carbon atom carrying a partial positive charge. Consequently, the electron pair in the carbon-halogen bond is pulled closer to the halogen atom. The hydroxide ion acts as a nucleophile and attacks the carbon atom bonded to the bromine. A curly arrow indicates the movement of the lone pair of electrons from the hydroxide ion to the carbon atom, forming a new bond. The bond between carbon and bromine is breaking while the bond between carbon and oxygen is forming. The bromide ion leaves, taking its bonding electrons with it. A curly arrow shows the movement of the bonding electrons from the carbon-bromine bond to the bromine atom. For SN1, the first step is the dissociation of the carbon-bromine bond in 2-bromopropane. The bromine atom leaves, taking the bonding electrons with it, and forms a bromide ion. This step is slow and results in the formation of a carbocation, an intermediate with a positive charge, at the carbon previously bonded to bromine. The hydroxide ion then attacks the carbocation. The lone pair of electrons on the hydroxide ion is donated to the positively charged carbon, forming a new bond. The name of the mechanism is nucleophilic substitution. In part D of question 3, we have that the student sets up an experiment to compare the rates of hydrolysis of 2-bromopropane and 2-iodopropane. The student places two test tubes, both containing aqueous silver nitrate and ethanol, in a water bath at 60 degrees Celsius. Then, the student adds 5 drops of 2-bromopropane to one test tube and 5 drops of 2-iodopropane to the other test tube and records the time taken for a precipitate to appear in each test tube. We have 2 questions. In the first question, we are asked to complete the given table to show the formula and color of each precipitate formed. As seen in the previous question, in the hydrolysis, the student is replacing the halogen by a hydroxyl group via nucleophilic substitution. The addition of aqueous silver nitrate precipitates the relevant silver halide. This is a typical identification reaction of halogens. The color of the precipitate and its solubility in ammonia allows to differentiate between them. Therefore, the formula of the precipitate with 2-bromopropane is silver bromide, AgBr, and the color is cream. In the case of 2-iodopropane is silver iodide, AgI. And the color is yellow. In the second question, we are asked to predict which precipitate would form first and explain the difference in the rates of hydrolysis of 2-bromopropane and 2-iodopropane. The experiment looks at how easily the bonds between carbon and the halogen in 2-bromopropane and 2-iodopropane break. The bond strength depends on the size of the halogen atom. Larger atoms make weaker bonds. Iodine is larger than bromine, so the carbon-iodine bond is weaker than the carbon-bromine bond. Because of this, the carbon-iodide bond breaks more easily, meaning that 2-iodopropane undergoes hydrolysis faster than 2-bromopropane. As a result, the yellow precipitate of silver iodide will form first. Question 4 is about the enthalpy change of combustion of alcohols. In Part A, we are asked to explain the term enthalpy change of combustion. By definition, the standard enthalpy change of combustion is the heat energy released when 1 mole of a substance undergoes complete combustion in excess oxygen under standard conditions, 25 degrees Celsius, 100 kilopascals pressure, with all reactants and products in their standard states. In Part B, the student carries out an experiment to determine the enthalpy change of combustion of butane-1-OL. We are provided with the setup, the apparatus of the student and the results. The student heats 200 grams of water by burning butane-1-OL with a spirit burner. The student measures the initial and final temperature of the water and the initial and final mass of the burner. In Part B, we have 3 questions. In the first question, we have the statement that the thermometer had an uncertainty of plus minus 0.25 degrees Celsius in each temperature reading, and we are asked to calculate the percentage uncertainty in the temperature change. Each temperature reading has an uncertainty of plus minus 0.25 degrees Celsius. Since there are 2 readings, initial and final, the total absolute uncertainty is 2 times 0.25, that is 0.50 degrees Celsius. The temperature measured by the student is the difference between the final and the initial temperature, that it is 31 degrees Celsius. The percentage uncertainty is the ratio between the absolute uncertainty and the measured value multiplied by 100. It is 1.61. In the second question of Part 4b, we are asked to use the student's results to determine the enthalpy change of combustion of butane-1-OL in kilojoules per mole. We are also asked to explain why this value is different from the data book value and suggest how the experimental design could be modified to improve the accuracy of the enthalpy change of combustion value obtained. I copy the drawing and the data that we need to answer the question. The heat used to increase the temperature of the water is obtained by multiplying the mass of the water by the heat capacity of the water from the data sheet and the difference in temperature. As the results are asked in kilojoules per mole, I express the results in kilojoules, getting 25.916 kilojoules. The mass of butane-1-OL consumed is 1.31 grams. Using the molar mass of butane-1-OL as 74.0 grams per mole, we obtain that 1.31 grams is 0.0177 moles of butane-1-OL. Dividing 25.916 kilojoules by 0.0177 moles, we get a value of 1464 kilojoules per mole. The difference from the book value can be attributed to several factors. Heat loss: heat escapes to the surroundings, air, burner, or calorimeter, instead of being fully transferred to the water. Incomplete combustion: butane 1-OL may burn partially, producing carbon monoxide instead of carbon dioxide, releasing less energy. Evaporation of fuel: some fuel evaporates before combustion, reducing the actual mass burned. Evaporation of water: some water evaporates, resulting in less than 200 grams. Standard conditions: data book uses standard conditions, 298 Kelvin and 100 kilopascal. The conditions during the experiment may differ. To improve the experimental values, consider the following modifications. Better isolation of the system: shield to protect from drafts or use a bomb calorimeter. Use a lid to prevent water evaporation. Use a metal can instead of a glass beaker to allow better heat transmission. Use an excess of oxygen. Reduce the gap between the burner and the beaker. Conduct the experiment under standard conditions, 298 Kelvin and 100 kilopascal. Increase the precision by using a balance with 3 decimal places or a digital thermometer. Heat for a longer duration of time to reduce percentage uncertainty in mass and temperature measurements. In the third question of question 4b, we have that another student carries out the same experiment using 150 grams of water instead of 200 grams. We are asked to calculate the mass of butane 1-OL that would produce the same temperature rise as in the previous experiment, assuming the same heat losses. As the amount of water has been reduced by 75%, the amount of butane 1-OL should be 75% of the initial quantity. The 75% of 1.31 grams is 0.9825 grams. Rounded to 2 decimal places, it is 0.98 grams. In part C of question 4, we have that the enthalpy change of combustion of ethanol in the gaseous state can be calculated using average bond enthalpies. We are provided with the reaction, the enthalpy change of combustion of ethanol and a table with average bond enthalpies. We are asked to calculate the average bond enthalpy of the carbon-oxygen double bond. The average bond enthalpy is the enthalpy required to break 1 mole of bonds in a gaseous molecule under standard conditions. Since breaking bonds requires energy, these values are always positive. The enthalpy change of combustion can be calculated as the difference between the sum of all the broken bonds and the sum of all the formed bonds. In the reaction given, we have the following broken bonds in the ethanol. 5 carbon-hydrogen bonds, giving a total of 2065 kilojoules. 1 carbon-carbon bond, giving a total of 347 kilojoules. 1 carbon-oxygen bond, giving a total of 358 kilojoules. 1 oxygen-hydrogen bond, giving a total of 464 kilojoules. In the oxygen, we have a double bond. As we have 3 oxygens, the total bond enthalpy is 1494 kilojoules. If we add all these numbers, we have that the total due to broken bonds is 4728 kilojoules. We have the following bonds formed. 2 carbon-oxygen double bond in the carbon dioxide. As we have 2 carbon dioxides, the total contribution is 4 times the average bond enthalpy of the carbon-oxygen double bond. We have 2 hydrogen-oxygen bonds for each water. As we have 3 waters, the total contribution is going to be 6 times 464 equals to 2784. Adding these, we get that the total formed bonds is 4 times the average bond enthalpy of the carbon-oxygen double bond plus 2784 kilojoules. If we replace these values in the equation, we get that minus 1276 equals to 4728 minus 4 times the average bond enthalpy of the carbon-oxygen double bond plus 2784. This give an average bond enthalpy of 805 kilojoules per mole. In the second question of question 4c, we have methoxymethane, an isomer of ethanol. We are given the combustion reaction of the methoxymethane, that is similar to the combustion of the ethanol. The enthalpy change of combustion for methoxymethane is more negative than for ethanol. We are asked to explain why the enthalpy change of combustion values are different, in terms of the bonds broken and the bonds formed. When comparing the two reactions, the only difference is the bonds broken in methoxymethane and ethanol, while the other components, and therefore bonds, are the same. Breaking bonds requires energy, positive value, and forming bonds releases energy, negative value. Therefore, we can conclude that methoxymethane needs less energy to break down than ethanol. The exam asks for an explanation and not for calculations, therefore, calculations are ignored for marking. However, we can calculate the average energy to break down the methanol and the methoxymethane to check that the methoxymethane required less energy. Doing the calculations as in the previous question, I get that to break 1 mole of methanol we need 3234 kilojoules and for methoxymethane we need 3194 kilojoules. Question 5 is about alkenes. In part A, a mixture of alkenes is produced when water is eliminated from alcohol A. We are given the structure of the alcohol. In the first question, we are asked what is the systematic name of alcohol A. The longest chain has 5 carbons, making it the main chain and naming it as pentane. There are 2 substituents, an alcohol and a methyl group. The alcohol group takes precedence. We number the chain starting from the end closest to the alcohol group, giving the O group the lowest number, which is 2. This results in the name pentane 2OL. Finally, we add the methyl group to the third carbon, resulting in the name 3-methylpentane 2OL. In the second question, the alcohol A is refluxed with an acid catalyst, producing a mixture of alkene isomers B, C, and D. Alkenes B and C show easy isomerism but alkene D does not. We are asked to construct the equation for the formation of alkene D from alcohol A, showing the structure of the organic product. The reflux of an alcohol with an acid catalyst produces an alkene. Besides, the question mentioned that they are alkenes. In this reaction, we have that the OH produces a carbon-carbon double bond and releases water. The double bond is going to be formed between the carbon 1 and carbon 2. Or between the carbon 2 and the carbon 3, giving the structures showing in the table of question 3. In this case, each carbon in the double bond has 2 different groups attached, and it is going to form the easy isomers B and C. Therefore, alkene D is the one with the double bond between carbon 1 and carbon 2, and the reaction is, don't forget the water. In question 3, we are given the skeletal formulae of alkenes B and C and asked to use the Kenangold-Prelog priority rules to explain why alkene B is the Z isomer. The Kenangold-Prelog priority rules are: first, we compare the atoms directly attached to the double-bonded carbons. The higher the atomic number, the higher the priority. For example, carbon has priority over hydrogen. Second, if the atoms are the same, we move to the next set of atoms along the chain until a difference is found. Multiple bonds are treated as if the bonded atoms are duplicated or triplicated. For example, a carbon-carbon double bond is considered as if there are 2 single bonds to the same carbon, and a carbon-carbon triple bond is treated as if there are 3 single bonds. we have that in Z isomers the higher priority groups are on the same side of the double bond, whereas in E isomers the higher priority groups are on opposite sides of the double bond. To see the priorities, I expand the bonds in alkene B and number the carbon atoms. I label one of the carbons as 3' to refer to it in the explanation. In alkene B, starting with carbon 2, we have that it is attached to the carbon 1 and to a hydrogen. As the carbon has higher atomic number, it takes priority. We continue with carbon 3. It is attached to 2 carbons, both have the same atomic number. We move to the next carbon on each side, carbon 4 and carbon 3'. Carbon 4 is attached to a carbon, carbon 5, and to a hydrogen. Carbon 3' is attached to 3 hydrogens. At this point, we have that the carbon number 5 has priority over the hydrogens. As it has higher atomic number, then the priority is in the branch of the carbon 5. In a nutshell, the priorities are given by the higher atomic numbers of the atoms attached to the carbons of the double bond. In the case of alkene B, the highest priority groups are in the same side. In part B of question 5, we are provided with a monomer to develop a water-soluble polymer. In the first question, we are asked to draw a section of the polymer formed, showing 2 repeat units, and suggest why this polymer is likely to be soluble in water. This is an addition polymerization, where the double bond in the monomer breaks and forms new bonds with adjacent monomers, creating a polymer chain. This polymer is likely to be water-soluble due to the presence of hydroxyl groups that can form hydrogen bonds with water molecules, which increases the solubility of the polymer in water. In the second question, we need to outline 2 ways that waste hydrocarbon polymers can be processed usefully, rather than being disposed of in landfill sites. There are several effective methods for processing waste hydrocarbon polymers to avoid landfill disposal. Recycling, where polymers are sorted, cleaned, and reprocessed into new products. Incineration, where waste polymers are incinerated to generate heat. This heat can be used to generate electricity or provide heating. Feedstock recycling, where waste polymers are chemically broken down into their basic chemical building blocks, which can then be used as raw materials, feedstock, for creating new products. And this is the end of the paper. If you want to see more videos like this, please click like, and leave a comment, as it will help me to carry on making more videos.